Okay, so like we said, we're going to talk about factored and standard form of polynomials with graphs. So a standard form, we'll start with quadratic and then we'll move into more of the polynomials you're going to work with. And the reason we'll do that is hopefully it like jogs your memory of stuff you would have done before. So we'll stay in function notation. So we'll say f at x is equal to the factor form we'll start with, okay? So usually there is some leading coefficient. There's some value that's outside of the brackets. And then you have x plus or minus something. It really doesn't matter. We could say minus, okay? And we'll call this letter, I've already used the letter A, so we'll put a B in here for factor form. And then x minus, we'll put a C here. And each of these represents a root, so B and C. So for instance, the graphical representation, this will be a little sketch of it, is let's say this is your B value. If they're negative, they're technically both positive values. And we have, assuming A is positive, we have some polynomial that looks like that. Now this one happens to be quadratic, okay? The standard form of this would be if you had decided to expand. So expanding is the concept of distributive property, or sometimes they call it FOIL. Rainbow method is where you take the x, you multiply it by both terms, take this negative b, multiply both terms, collect like terms, and you end up with something that looks like this. You'll notice the a value stays the exact same, and then you have a variable to the power of whatever this polynomial is. This one's quadratic, so it happens to be 2. Okay, and if you notice there's 2 x's, so that kind of corresponds with it. Plus, usually there's some other coefficient b. Not to be confused with their b above. Maybe I used the wrong letters. I'm going to use different letters because they don't technically mean the same. Get out of here. Let's say, let's call it R and S. Does that work for you?
Yeah.
We'll call it R and S. Okay, so this is maybe R and S in this case. So this is a quadratic representation. There is to the power of 2. But this factored, and then the second one is standard form. So write that in here. This is standard, and this is factored. But we can have polynomials of larger degrees. And what we mean by that is the leading exponent on the variable could be much larger, and we can write it in the very similar form. So I'll call this g at x because technically it's different from the above function. The above function represents a quadratic. In this one, it's a cubic function. You can still usually come out with some leading coefficient, and then you have x minus something, x minus something, x, well, I mean, we could say plus. We'll say minus every time because it does help if we're given specific roots to start with that. We'll call this r, s, q, r, s, t. Okay, and then this one in its standard form, if you go through distributive property again, you'll notice the a value stays the same, but this time it's a x to the power of 3 because there are 3 variables here. Then we would have b to the power of 2 plus maybe, oh my god, I forgot the alphabet, c with x. X is technically to the power of 1, we just don't write it in. And then plus, we'll call this letter D, okay? Using that same idea, we can write, again, this is our factored, okay? This is our standard. We can continue to make larger and larger polynomials. All we have to do is essentially add sets of brackets. Every time we add a set of bracket, this exponent increases. So if we end up with brackets with 4 x's, this becomes power of 4, and then we can go 4, 3, 2, 1, and add a constant at the end. If we add another bracket, that'd be a quintic function, which has 5. 5, 4, 3, 2, 1 in the standard form. So one of the things that you're working on is polynomial division, which is actually a form of factoring. It's taking this and putting it into factor form. So they'll call this polynomial division. Now the question becomes, why do that? Why change back and forth? What's the point of it? If you're going to graph, the standard form is a bit tricky. It doesn't really give you a lot of information about the graph. It does give you a y-intercept. In this case, the c would be the y-intercept, so that's where it crosses this y-axis. In this one, it would be our letter d. It's essentially whatever the constant is. Whatever the constant value is, that's your y-intercept. That's lovely, except I can't draw much off of a y-intercept. Like if I know a y-intercept's here, I have no idea the rest of the function. Does it have lots of roots? Which way does it go? Like, it's not a lot of graphical information. However, your factored form gives you all of these roots, okay? So with all of these roots, if I have two of them and then I look at A, I should mention A is in this one too, so it does tell you if it is a even valued polynomial. Maybe we should touch on that actually before I talk about the A. I'm going to go on a little diversion here. Technically, so I'll draw parent functions. A parent function is a function that doesn't actually have all of these extras in it. It's like the bare minimum of a function. So a parent function for a line, we'll call this L at x for line. Oh, that's not the tool I want. There we go. We'll call this L at x, okay? This represents a line. It's just x. And that is actually just a line that goes in this direction, okay? Knowing that is going to be really helpful. And same with this one. For a quadratic, we'll call it q at x for quadratic is equal to x squared. That has a general graph like this. All right, got it. Okay. So we got those two. Those two are the bases. What's really important is noticing that the exponent here is odd and the exponent here is even. That actually gives you a lot of information about this. So there's another function called cubic. I'll use c. C at x for cubic is x to the power of 3. And it does something like this. I didn't draw that very well. It's supposed to cross through the middle there, the parent function. But I want you to notice that its general trend is the same as the linear function, okay, because it's positive at the moment. And quartic, that's another q. That's interesting. We use so many q's. Let's give it an r. The r is kind of prominent there. We'll call it qr. Maybe that helps a bit. X to the power of 4. That actually makes... The parent function doesn't make a w, but it does something like this. It kind of goes like this and goes upwards. And if you notice, that's similar to the quadratic. A quadratic has that shape to it. And as we continue to add the exponent, or we shouldn't say add it, but it grows larger and larger, your functions do the exact same stuff. A quintic function actually goes up 1, 2, 3, 4, 5 and comes up, where a cubic goes up 1, 2, 3, and a linear just goes through once. So these degrees here can actually tell you how many potential roots. There could be less, but that's the maximum potential roots there are. So a quadratic, it could cut through 1, 2 times. Linear is just once. Cubic goes 1, 2, 3. Quartic can go 1, 2, 3, 4. Quintic can go 1, 2, 3, 4, 5 and goes up. But all your odd ones kind of end in this direction, and all your even ones kind of have this like U shape with maybe some funny stuff happening at the bottom. Okay, so we'll keep that in mind. So as we digress, we'll go back here. This A value here tells you which way they open. So if they happen to be negative, your linear line, okay, let's do this in a different color, would actually go from here, top left to bottom right. If you have a negative cubic function, it does the same idea. Kind of goes down, up, and down again. Follows that line. If it's quadratic, it goes down like this. If it's quartic and it's negative, it goes down like this. So that A value tells you which way it opens, okay? So it's a very messy graph now, not very helpful at the moment. But as we went through it, hopefully it made some sense. So we got our y-intercepts, and then these ones give us all of our x-intercepts, okay? So whatever these values are, that's the points that they're crossing and how many of them there are. So it's important to realize that. And some of them have different powers to them, which means they have different behaviors as they cross. So we'll talk about more about those. But we'll go take a look at this graph here. This is the one we had. So we had an example of a quadratic. And if we notice, it represents, or it relates here to these values. We have positive 1 and negative 2, and it turns out we get positive 2 and negative 1 as our roots. As we turn on this one, which has 3, we had positive 1, negative 2, and then positive 3. That's in here. But when we think about the roots, we have to think about the opposite of those values. So it becomes negative 3, negative 1, and positive 2. Okay? This one becomes quartic. Has that W. It's not a lovely looking W, but same thing. You'll notice it's crossing the same points, but different behaviors in the end. We can take this exact same function, and let's make it the 5. Let's put one on the other end here. Let's say x, I don't know, minus 5. There we go. I mean, it's getting some really funny end behavior there. But this is, let me zoom out enough. Here, let's do this. I'll change the parameters. so we can get a better view of it. We're going to say the x values will go from negative 10, 10 to positive 10, but the y values will be much larger. Let's go to 100 and maybe negative 100. Do we get a bit of a view? Yeah, we're starting to see it a little better. See how that, oh, wow, this one really moves. There we go. It goes up. Can I draw over this? I think I can. Oh, no, I can't. I'll use this instead. You'll see it goes up 1, 2, 3, 4, and then all the way down 5. So it crosses at 5 points, and that's why you end up with like your x to the power of 5 in that case. Okay. Okay.
Does it matter how low it goes? Because my teacher said like not really, but I don't know.
It doesn't particularly. I mean, all of them are gonna have different behaviors depending on. I'll turn this piece off. What your a values are. As part of it. That's going to make a big difference. So let's see if I turn it to double. See how it got even larger?
Yeah.
It's being vertically stretched, if you remember like a quadratic. So if I put it to like 4, very stretched. We got to zoom way out even farther. Okay? If I actually make it a half, it looks like a compression. So everything got a little more compressed. Let's get rid of that piece there. See how everything got a lot more compressed? That a value still has the same effect as if we're transforming a quadratic. With the other polynomials, we have vertical stretches and compressions as part of it. Okay, and then technically we could still have the same transformations. Like if I go plus 8, this whole thing, let's see if it moves up from some, oh, we're so far zoomed out, I didn't realize 8 won't really show. Let's say plus 80. There you go. Looks like it's just been shifted up 80. So a lot of those same transformation rules, they all apply to these. Okay, it's just taking those rules we learned with quadratics and applying them to polynomials that we're probably not as familiar with.